Hello everyone, my name is Shady. I am presenting our work on improving the performance of off-the-shelf deep super resolvers. The single image super resolution acquisition model can be formulated as convolving an image X with a Blair kernel K followed by subsampling with some scale factor alpha to get the observed image Y. Such model can be written more elegantly using operator form, where S star encapsulates the entire downsampling operation. The problem of single image super resolution can be defined as retrieving the high resolution image X from the low resolution image Y. Over the past decade, many deep learning approaches have been proposed for solving such an inverse problem. They usually take an image downsampled with the bicubic kernel, then train the neural network to map it to the high-resolution version of it. Because deep neural networks are often trained using a single Blair kernel, their performance degrades significantly when examined on other kernels, as it can be seen from the following example. In this work, we propose to apply some filter H on the observed low-resolution image that transforms it into the low-resolution bicubic image. This leads to the following sampling and reconstruction system from the theory of generalized sampling. Assuming that X is in the range of the projection onto R and that the null space of S star does not intersect with the range of R, we have a perfect reconstruction of X using the following H, which is equal to the inverse of K convolved with a bicubic kernel followed by subsampling. For super resolution, we replace the reconstruction part of the system with the SR network. Although for most of the real-world images, X is not in the range of the projection onto R, we are still getting significant improvement compared to other methods. Here we can see an example that demonstrates the promise of our method. We downsample an image using Gaussian blur, then apply three different state-of-the-art super-resolution networks trained with a bicubic kernel: ProSR, Arcan, and DBPN. It can be seen that their performance is quite poor. Yet, when they are used with our method, a significant improvement can be seen, even though all these networks were trained only with a bicubic kernel. We also compare our method to SRMD and ZSSR, where both of them take the downsampling kernel as an input in addition to Y. Similarly, we show the remarkable improvement of our method also for scale factor of 4. In numbers, here we can see the performance improvement on set 14 for Gaussian and box filters. In some cases, we see almost 7 dB improvement in PSNR compared to not using the correction filter. We perform similar tests on the BSD100 dataset, and a similar boost in performance is achieved. In many cases, the sampling kernel K is unknown, and therefore we cannot use the analytic expression of the correction filter H. Therefore, we present an algorithm for estimating the correction filter when K is unknown. We do that by minimizing the following objective function using K. The first term is for consistency, the second is for centralizing the estimated kernel K, and the last promotes sparsity. This leads to the following iterative scheme. We take the observed image Y and convolve it with H from the expression we saw previously. Then we upsample it using a pre-trained SRDNN for estimating the latent image X. That is then downsampled using K to get Y hat, which we require to be as close as possible to Y. Here, we see an example that demonstrates the blind super-resolution performance on a non-bicubic degraded image. We see that we outperform kernel GAN, which is a recent method based on adversarial learning for blind super-resolution. Similarly, we see significant improvement in our method compared to others also in the scale factor of 4. Here we can see the results in numbers for set 14 for multiple downsampling kernels. The same holds for BSD100 and the recent Div2K arcade dataset. Finally, our code is available online. Please check it.